brings us to the core problem, doesn't it? How do we actually see this invisible structure? We obviously can't just stare at a solid block of steel and magically know its atomic layout. And standard microscopes? Yeah, they don't help either, because atoms are just too small for visible light to catch. So we need a special kind of detective tool. We basically have to interrogate the material. We need to bounce something off of it that's exactly the right size to squeeze through those microscopic corridors of its atomic structure, and then report back to us with the floor plan. And well, that is exactly where X-rays come in. Here is our roadmap for today's explainer. We'll start with the mystery of matter, then move right into how XRD actually works, look at the superpowers of XRD, cover the tool's blind spots, and finally, wrap up with real-world applications. Section 1. The mystery of matter. All right, the crucial thing to understand right off the bat is that XRD is basically the master key. It unlocks the hidden structural secrets of a material's atomic makeup. When scientists run this technique, they're really hunting for three primary things. First up, atomic spacing, literally the exact physical distance between the atoms inside a crystal. Second, the crystal structure, so how are those atoms geometrically arranged and stacked together? And third, the phase composition, which tells us exactly what different crystalline compounds are mixed up inside that specific material. Honestly, without this data, we're flying completely blind in material science, chemistry, and geology.
Moving on to Section 2, how XRD actually works.
The whole process is actually incredibly elegant when you break down the logic. It happens in three basic steps. Step 1. An X-ray source fires a beam of incident X-rays directly at our material. Simple enough. Step 2. Those X-rays hit the sample. But here's the trick. They don't just hit it straight on. They hit it at a very specific, carefully measured angle, which we call theta. Now, when these X-rays hit the regularly spaced atoms in the crystal, they bounce off, or diffract, scattering in very specific directions. Finally, Step 3. A super-sensitive detector is perfectly positioned to catch and measure all those diffracted X-rays as they ricochet off the sample. And this whole setup beautifully illustrates exactly what we were just talking about. You've got the X-ray source firing those incident X-rays down at the sample. Notice that specific angle, theta. Then the X-rays bounce off, creating these diffracted X-rays that travel straight up to the detector. It is literally geometry in motion. As the machine continuously sweeps through different angles, moving both the source and the detector, it measures where the X-rays bounce strongly and where they just don't. That physical mechanism translates directly into the data output. Now, that data output, that's called a diffractogram. You can really just think of this as the ultimate fingerprint of the material. A diffractogram is a chart that maps the intensity of the X-rays on the vertical axis against the diffraction angle, usually noted as 2 theta, on the horizontal axis. When you're looking at that chart, you'll see a distinct series of peaks and valleys. Those specific peaks, their exact height and their location on the graph, act as a completely unique mathematical signature for the material's internal structure. It's a fundamental rule. No two unique crystal structures will ever produce the exact same diffractogram. Which brings us to Section 3, the superpowers of XRD. One truly incredible metric here is this number, 20 minutes. I mean, think about that. That is incredibly fast for atomic-level analysis. One of the biggest advantages of XRD is just its raw speed. Sure, some super complex analyses might take a bit longer, but routine measurements, they can usually be totally wrapped up in under 20 minutes. This lightning-fast turnaround is absolutely crucial for things like quality control in manufacturing or in high-volume research labs where, you might need to blast through dozens of samples in a single afternoon. But beyond just speed, XRD boasts some serious capabilities. It gives us unmatched precision when we're measuring atomic spacing and remarkably high accuracy for determining crystal structures and phase composition. And honestly, it is so versatile. It has this extremely wide applicability, whether you're dealing with loose powders, solid chunks of metal, fragile thin films, raw minerals straight from the ground, or advanced ceramics. Basically, as long as it has a crystalline structure, XRD can usually analyze it. But here's where we run into a really fascinating paradox with these superpowers. XRD is famous for being a non-destructive analysis technique. The X-rays just pass through and bounce off the material without altering its chemistry or destroying it. So your sample remains totally intact and reusable, right? Well, there's a catch when it comes to sample preparation.
To get the absolute best, cleanest data, bulk samples usually need to be finely ground up into a homogeneous powder. So while the X-rays themselves won't destroy the powder, the actual act of preparing the sample might require you to fundamentally destroy the original form of your bulk object. It's a kind of ironic trade-off you always have to keep in mind.
All right, let's look at Section 4, the tool's blind spots.
First up is the sensitivity limit, which sits around 2%. Here's the deal. If you have a mixture of different crystalline phases in your sample, XRD is fantastic at identifying the main ingredients. But trace phases, meaning materials that make up less than roughly 2% of the overall mixture, are notoriously tricky to detect. They simply don't throw off a strong enough signal to stand out from the background noise on the diffractogram. So if you're looking for a needle in a haystack, and that needle makes up less than 2% of the stack, XRD might just let it slip right past the detector completely unnoticed.
The next blind spot really comes down to how we interpret the data. Remember earlier when we called the diffractogram a fingerprint? Well, think about it. A fingerprint is utterly useless if you don't have a database to match it against. The exact same logic applies here. To identify unknown phases in your sample, you absolutely require a reference database of standard diffraction patterns. The whole identification process depends entirely on comparing your fresh data with those established databases. If you've somehow synthesized a completely brand new, never-before-seen material that isn't in any database yet, XRD will give you a beautiful, crisp pattern. But it won't be able to just tell you what the material's name is without some intense mathematical legwork.
And then we have the ultimate blind spot. XRD relies completely on the regular, ordered, repeating patterns of crystalline structures to bounce those X-rays in a predictable way. Because of that, it is completely unsuitable for amorphous materials. It just cannot accurately characterize non-crystalline or poorly ordered materials. We're talking about things like standard glass, a lot of polymers, or liquids. If the atoms are just jumbled together randomly without a repeating pattern, you're not going to get those sharp, identifiable peaks on your diffractogram. The X-rays will literally just scatter into a messy, unreadable blur.
Let's wrap up with Section 5, Real-World Applications. Let's see how all of this builds into an incredible array of scientific disciplines, because XRD is a true workhorse. For chemists, it's their go-to for phase identification and deep crystal structure analysis. Need to figure out exactly how large individual microscopic grains are? It easily handles crystallite size estimation. Meanwhile, engineers rely on it heavily for strain and stress measurement, literally checking to see if a metal is dangerously fatigued at the atomic level. It's also absolutely crucial for thin film characterization in the semiconductor industry, which, by the way, is what ensures your computer chips actually work properly. And of course, it is a foundational tool in mineralogy and geology, whether you're identifying rocks pulled from deep inside the Earth or even samples drilled right out of the surface of Mars.
So, we've covered the amazing advantages, the inherent disadvantages, the incredibly ingenious mechanism, and the vast applications of X-ray diffraction. It truly is a remarkable window into the atomic architecture of our universe. But it leaves us with this really fascinating thought. If XRD can so elegantly decode the rigid, ordered crystalline world, what other invisible structures, perhaps the messy, amorphous ones, or wildly complex biological structures, are just waiting to be uncovered by the next great leap in technology? The universe is built atom by atom, and honestly, our quest to understand it is really just getting started. Thank you so much for joining me on this explainer today. Keep asking questions, and as always, keep exploring the invisible world.